Welcome. So this session we are going to check how to verify that given functions are solution to given differential equations. Let's start with appetizer. So one, verify that y equals to e raised power x is a solution of the differential equation dy dx equals to y. Now, one way of verifying that a given function is a solution to a given differential equation is to simply differentiate the function and then substitute into the equation or into the given differential equation to show that we get an identity. So this is what I mean. For instance, in this case, y equals to e raised power x is given. So dy dx, this implies that dy dx, if you differentiate an exponential, you get e raised power x. So clearly, dy dx, which is the same as e raised power x, is the same as y. So y equals to e raised power x is a solution. Number two, show that y equals to e raised power minus 2x is a solution of the differential equation y prime plus 2y equals to 0. To solve this, so we have y equals to e raised power minus 2x is given. So which implies that y prime, differentiating this function by chain rule, we get negative 2 e raised power negative 2x. Now replacing in the equation given, we have y prime plus 2y is negative 2 e raised power minus 2x plus 2, y is e raised power minus 2x, which is the same as minus 2 plus 2 e raised power minus 2x, which is the same as 0 times e raised power minus 2x, which is 0. So clearly, left-hand side equals to right-hand side equals to 0. Hence, y equals to e raised power minus 2x is solution to y prime minus 2y equals to 0. Number 3, show that y equals to c e raised power minus 2x is a solution to the differential equation y prime plus 2y equals to 0, where c is any constant. Now, to verify this, y equals to c e raised to minus 2x is given, which means y prime is minus 2c e raised to minus 2x. Substituting gives y prime plus 2y equals to minus 2c e raised to minus 2x plus 2 into c e raised to minus 2x. What is the value of y? This will give us minus 2c e raised to minus 2x plus 2c e raised to minus 2x, which is the same as minus 2c plus 2c multiplied by e raised to minus 2x. And this is 0 times e raised to minus 2x, which is 0. So i.e. y equals to e raised to minus 2x, say e raised to minus 2x is a solution to y prime plus 2y equals to 0, because you can clearly see that the equation is satisfied. Number 3 or 4, verify that y equals to a cos x plus b sin x is a solution to d squared y dx squared plus y equals to 0. Now solution. So y equals to a cos x plus b sin x. This is given. Then dy dx will be negative a sin x plus b cos x, which implies second derivative is negative a cos x minus b sin x. Now substituting, we have d squared y dx squared plus y equals to negative a cos x minus b sin x plus a cos x plus b sin x, which is negative a cos x plus a cos x minus b sin x plus b sin x. And clearly this is 0. So therefore, y equals to a cos x plus b sin x is a solution to this differential equation. And then next one, verify that. Number 5, verify that y equals to x e raised to power x is a solution to the differential equation y double prime minus 2y prime plus y equals to 0. Now, solution or the proof for this, y is x e raised to x. This is given. So y prime, now these are product, so we'll use product rule, u prime v plus v prime u. So where you get u to be x and v to be e raised power x. So u prime is 1 times v, we get e raised power x. And then v prime is e raised power x times u, x e raised power x. Now, second derivative will be, this one gives us x, and this one gives e raised power x plus x e raised power x. So substituting, we get y double prime minus 2y prime plus y will be e raised power x plus e raised power x plus x e raised power x. This for y double prime minus twice y prime is e raised power x plus x e raised power x. And then y is x e raised power x. So this will give us 2 e raised power x plus x e raised power x minus 2 e raised power x minus 2 x e raised power x plus x e raised power x, which will be 2 e raised power x minus 2 e raised power x. Now this plus this gives us 2x e raised power x and then minus 2x e raised power x. Clearly you see that this is 0, this will be 0, so this ends up to be 0. So left hand side equals to right hand side equals to 0, and therefore y equals to x e raised power x is a solution to this differential equation. So next example. Show that x equals to x1 equals to c1 cos 4t and x2 equals to c2 sin 4t are solutions to this differential equation. Now, solution x1 is a solution means x1 double prime plus 16x1 should be 0. We check that this is true. So x1 is c1 cos 4t, which implies x1 prime will be minus 4 c1 sin 4t, which implies x1 double prime equals to negative 4 by 4 is 16 c1 cos of 4t. Remember here we are using chain rule for differentiation. So substituting, so x1 double prime plus 16 x1 will be negative 16 c1 cos 4t plus 16 into x1 is c1 cos of 4t. which will be negative 16c1 cos 4t plus 16c1 cos 4t, and clearly this is 0. So since left-hand side is the same as right-hand side equals to 0, this implies x1 is a solution to this differential equation. And then x2 is given by c2 sine of 4t, which implies x2 prime is 4c2 cosine of 4t. Now remember, we are using chain rule for differentiation. x2 double prime will be negative 16 sine 4t. So substituting, we have x2 double prime plus 16, x2 is minus 16, as I c2 here, c2 sine 4t plus 16 into c2 sine 4t. So which will be minus 16 c2 sine 4t plus 16 c2 sine 4t. And clearly this will be 0. Now left-hand side equals to right-hand side equals to 0. So this means x2 equals to c2 sine 4t is a solution. Solution to this differential equation. Now, lastly, show that every member of the family of functions y equals to c over x plus 2 is a solution of the first order differential equation dy dx equals to 1 over x into 2 minus y on the interval 0 to infinity, where c is a constant. So this is a very easy problem. What we're just supposed to do is to differentiate the function and replace into the differential equation to show that the two sides are the same. So solution, we have y equals to c over x plus 2, which is the same thing as saying y equals to c x raised to negative 1 plus 2. So that means dy dx will be negative c x raised to minus 2, because now just using power rule, derivative of constant is 0. So this is what we have, which is the same as negative c over x squared. So substituting into dy dx, we get negative c over x squared So this is what we have as our differential equation. And then we have to show that this is the same as 1 into 2 minus y is given by c over x plus 2 So this is what we have to show. So we need to verify this. Or maybe let's just say this is what we have. So we verify that. We don't give the conclusion first. So verify that negative c over x squared is equals to 1 over x into 2 minus y. So this is what you have to be there, because we are told that dy dx is 1 over x into 2 minus y. So since y is given by c over x plus 2, then it implies that 2 minus y is equals to 2 minus c over x plus 2, which is the same as 2 minus c over x minus 2, which is b minus c over x. Now, 1 over x into 2 minus y. So this implies will be given by 1 over x times 2 minus y, we have gotten to be minus c over x, which is minus c over x squared. And clearly, left-hand side, which is given by minus c over x squared, is the same as right-hand side, which has been reduced to negative c over x squared. So therefore, every value of c, the function, y equals to c over x plus 2 is a solution to the given differential equation. So that is how easily we prove that a given function is a solution to a given differential equation. Just differentiate the function, and once you have differentiated the function, you replace the function and its derivatives into the differential equation and check whether you are getting an identity. If that is the case, then the function is a solution. If the equation is not satisfied, then you conclude that the function given is not a solution to that specified differential equation. Thank you.